part of this presentation, some inputs I also received from Henrik Thorsen, who is the CEO of the Energy Cool company that is also a partner at the cities project. So this presentation will actually consist of 3 parts. The first one is the work that we carried out at Singapore, where we focused on district cooling potential. So as we have lots of expertise in Denmark with district heating, that can be quite useful for district cooling also, that has many similarities. We have done this in collaboration with Nanyang Technological University, where we established potential for using the district cooling on a systematic scale. Following that, we will move to a demo case that was also part of the cities project, where we are testing an absorption chiller at GEV at Greenstall, a district heating utility. And then we will finish up with actually a new project, a large one funded by the Innovation Fund Denmark that started just 2 months ago. That is actually an important continuation of the cities project. So to give you a brief introduction to Singapore, to understand it better, you can see that Singapore is located in the southeast part of Asia, very close to the equator. It's a city-state of only 720 square kilometers, but having approximately 6.5 million people on that small land area. They are very well economically developed, having the 3rd GDP at power purchase parity per capita in the world. And what is actually extremely important for the district cooling studies that they have a very uniform temperature variation. So their temperature during the whole year is between 24 and 32 degrees. So day and night, the whole year. What is interesting about their energy system? So they consume around 40% of their greenhouse gas emissions comes from the power sector, and around 40% actually of their power consumption goes for cooling. So they have incredibly large energy demand for cooling throughout the whole year, because of course, the high temperatures, constant high temperatures, and a high humidity. What we can see on the right side is that in their electricity generation mix, they get 95% of their electricity from natural gas. So right now, they produce almost all of the electricity from natural gas, which has approximately efficiency of around 50%. So they're wasting actually 50% of their heat, not utilizing it at any point. And that's the problem that we tackled in this research. This is just to show you how they don't have actually a variation in demand, so no seasonality. The upper figure, it's the electricity demand throughout the whole year, so it's very uniform. And then you can see a pattern of 2 weeks in the lower figure, where we can clearly see that there is a difference between work days and weekends. But other than that, very uniform electricity consumption data. So what is actually district cooling? So it's a central production of cooling energy, and that part is similar to the heating energy. There are 2 main different approaches. One is that we have actually centrally produced chilled water that we distribute via the pipes. And the other more common maybe approach in Europe, in Northern Europe, is to use district heating network, where we then produce chilled water at the end user side. If we do it as centrally distributed chilled water, which is more common approach in warm areas, we usually have a supply temperature of between 6 and 12 degrees and a return of around 18 degrees. So this is actually one very important distinction from a district heating system, that we have temperature difference of only around 12 degrees, which is much smaller than district heating grid, which has a temperature difference of 40 to 50 degrees. And the important consequence of this is that district cooling piping needs to be around 3 to 4 times larger diameter than district heating piping. And then we come to what could be actually sources of energy for this district cooling. In Singapore, one good source of direct cooling is actually a liquefied natural gas gasification terminal that releases approximately 0.23 kilowatt hours of cooling per kilogram of liquefied natural gas that is regasified in the terminal. The second and the third option are electric chillers and absorption chillers. The electric chillers are the usual cooling devices that are used all over the world, while absorption chillers are very interesting because they can use actually a heat source at approximately 70 degrees or above to produce chilled water. Their coefficient of performance is usually around 0.7. Our methods in Singapore consisted of locating potential resources for cooling energy production, calculating cooling demand in the considered area, then establishing a GIS-based grid layout, making detailed hydraulic calculation and dimensioning of the grid, and then calculating socio-economic costs, producing different indicators and comparing it with the business as usual scenario. So now you can see the state or the city of Singapore with all the power plants and waste incineration plants, as well as the LNG terminal that are actually potential sources of waste heat that can be used in those absorption chillers for production of chilled water. We can see that we have one plant located in the northern part, and then many plants located in the southwest part of Singapore. So if we focus a bit more on the southwest part, after this GIS mapping, we can get something that looks like this. So the purple area here is actually a new business development that is planned in Singapore in a very large area. And that's what we found to be a perfect match, because it is something that is being delivered now, where district cooling could cover large parts of the actually cooling demand in this area. Here you can see this yellow marked line, which would be the transmission cooling lines, and black lines, which would be a distribution cooling lines. When we get a simplified representation, we get something like this. So we have lots of pipes with different dimensions, different diameters, different friction and flow rates within the pipes, which then can be simulated to calculate the potential cooling grid of Singapore. And these are actually the results of that part of the work. So we can see that approximately 17 to 18 terawatt hours of cooling energy we could cover just by using that waste heat that is now being wasted. So this is really a significant amount of energy, and actually a complete lack of energy efficiency in the system. And this could save approximately 8 terawatt hours of electricity based, of course, on the equipment that is used for the cooling generation. Just to put it in perspective, the current total yearly consumption of electricity in Singapore is 50 terawatt hours. So this is really an important share that could be saved. And this could then result in a CO2 reduction of almost 20%, in the same time reducing the total socio-economic costs. But what is actually the relevance and the impact in general is that we really need to raise the awareness that waste heat can be valuable even during the summertime. It is often being said in Denmark, for example, that during the summer there is excess of waste heat and that we cannot really use it. But this is actually one use case where we can see that this waste heat can be utilized actually for cooling production, which is relevant for Europe during the summertime. It's of course nice that, this work actually continued, and the group there and the professor Alessandro Romagnoli continued working on this. They moved to the more near-term applications where they are starting with the cryogenic cooling using the LNG regasification tool, which is a recent project that they got awarded. And this work also continued in a group with numerous further publications on cooling. Continuing, just if someone wants to see more detailed results, there are two publications that were part of this work, and the one in applied energy is actually published under the open access, so it's freely available to everyone. And then we moved to the demonstration case that was part of the CITES project. It started relatively recently in this year, where we are actually testing one of those absorption chillers that I mentioned at the GEV Greenstall site. So as I mentioned previously, that's a district heating utility that generates heating. And we are now testing one of the absorption chiller units that you can see in two figures on the right side, together with a small heat buffer tank. And we are producing chilled water from the district heating supply. And right now we are testing the solution at the meeting rooms on site. But the idea is that in the future we will actually, after the testing phase, use these absorption chillers for producing cooling for the data center that is located also on site. This absorption chiller is produced by a Danish company called Purex. And in this demo case, we have also partners in the Energy Cool company. So here we can also see that we already have data in our cloud that we can receive from site. And this demonstration project is still ongoing. The main goals are to have a flexible operation of this cooling based on price and CO2 signals, and to try to estimate potential of using both electric and absorption chillers interchangeably. And this demonstration project should be finished by the end of this year. And then the final part of the presentation is actually a focus on the future. And that's actually a cool data project that I mentioned we just got received this year. It is a 3-year project that started only a couple of months ago. And the main goal here is to produce AI-based, modular, and reliable cooling solution. And in this project, we focus on small and medium-sized data centers. So this is one part of data center industry where we realized that was really kept outside of the focus, and that is very under-optimized in their cooling. We have two locations where we will test our solution. The project consists of 8 partners, you can see a website that will be soon set up. And the project got the funding by the Innovation Fund Denmark. To speed up, I will here present only one more slide with the case study at Greenstall. That is one of our two demonstration sites, and the other one is Navy Air, that is Danish airspace control. So here we will test electric chillers, absorption chillers. We will develop phase change material storage that will be developed at DTU Civil Engineering. We will have options of using several cooling supply options. And what is very important, that we will actually capture the waste heat. And with the use of air-to-water heat pump, we will have options either to directly heat the nearby storage building, or to supply this heat back to the district heating grid. So this could be very interesting for many district heating companies in Denmark, because here we can see that they can be actually a provider of energy for producing cooling, and then back to receive the waste heat that is generated as a part of that cooling process. This was all for me. I will be more than happy to receive your questions. And if anyone is interested also in this new project that is a sort of continuation of the cities project, be more than free to contact me for some further information.
Thank you so much, Dominik. We have already a question from Henrik, and as we haven't got any else, I will retain my question to you and pass over to Henrik. Henrik, you have written it, but you're welcome to just say it. Thank you.
Yeah, when I listed the savings in CO2 or cost cooling of data centers in my list this morning, I mentioned up to 90% for data centers. Can you elaborate a little bit on that? Because now you are running this large project, Cool Data. Can you detail that on small, medium, large data centers, or maybe can Henrik Thorsen say something about potential savings? Or
yes, so this saving was actually calculated based on this case of GEV at Greenstall, where the first problem there is that we didn't use any free coolers at that site. Free cooler is actually just a simple unit, a fan that blows the cold air from outside to the server room when the temperature outside is usually below 10 degrees. So for example, in the winter time, it is not very smart to generate all the cooling energy from electricity if we, for example, have 0 degrees air outside. So in the first phase, we need to use this almost free energy. So this is actually the main source of these savings. And then the other important source is that if we have storage, cold storage next to the server room, which is very often the case because server rooms have important prerequisites on security and reliability of operation, that we can use this storage to smartly control our production of chilled water. So in the time when we have low CO2 intensity in the grid, we can generate more cooling energy, and then vice versa, when we have very high CO2 intensity in the grid, we will of course produce less chilled water. So those are actually the two main sources how we can significantly reduce the CO2 footprint, especially for those small data centers that usually operate rather suboptimal.